everyone, and welcome to our presentation on eliminating hidden risks in steam supply and pressure reduction systems, presented by myself and Tracy Snow.
Hello.
But first of all, please understand that we're going to present tips and guidelines today, but it's impossible to know every single application, so none of the webinar should be considered as a specific recommendation. Please read or take a screenshot of the disclaimer. And if you have a specific application, we're more than willing to help you and answer that. Right now, Tracy and I are going to turn off our cameras and we're going to proceed with the rest of the webinar. When I come to plants, I ask them about their steam and they say we've got superheated steam and saturated steam. Think about what a beautiful heat resource this is. It's very forgiving and it provides the high quality heat that you need for your production applications. But we also want to have risk mitigation. So when we take a look at the different variables for risk, you have a consequence of failure or the probability of failure. We can't change the consequence of failure unless you change the system design. But you can adjust the probability of failure. Once you take a look at your acceptance threshold, you can take various proactive actions to reduce the risk. And that's what we're going to talk about today. If you want to read more about a risk-based methodology for steam systems, please read Dr. Kane's risk-based methodology from Inspectioneering Journal. It's on the TLV.com website. Let's take a look at our steam heat asset. We're going to generate, distribute, use, and return the condensate from the steam system. We want to get dry steam so that we can optimize the heat to our production asset. We want to drain the condensate fast out of the equipment so that we're getting really the steam heat on the heat transfer surface. And we want to recover the condensate because it's got an energy benefit. This particular part of the webinar is going to focus on the dry steam aspect. We think of our utility mains like this. We've got steam running across the main, the top of the main, and at the bottom, condensate has fallen down and collected, and it's going to be transported along the pipeline, can be transported at high velocity, and if we don't drain it, we can get a water hammer event. So we know we've got to drain it through adequate size collecting legs. And this is a drip pocket and collecting leg with the trap and valves, because this is what the inside of the system looks like. You've got the condensate flowing down, and we need a place for the condensate to fall out. It's already been disentrained from the steam. We need a place to collect it and drain it. So ASHRAE makes a wonderful table, and we like to use the ASHRAE table. People pay attention to the D1 dimension. They know that the collecting leg has to be an adequate diameter so condensate can fall into it, but they don't often pay attention to the L dimension. I can't tell you how many times I've been on sites and that L dimension before the D2 takeoff is only about 2 inches. That's not enough of a reservoir. We need more of a reservoir so that L dimension and the D1 dimension, they're both critical. We also like to see a drop down to a trap. A lot of times we'll see people take that D2 dimension and just go straight into the trap. But traps actually work better when they have a water seal on them, and you get a better reliability in life if you have a drop down to the trap. So we always recommend that. This is what I call the trouble indicator when I take a look at a trap's survey history and their reactive or proactive response to steam trap management. When we see the good traps down so low, 38%, we already know this is going to be a huge trouble indicator. If you notice, they've had gap years, they haven't really had a proactive, sustainable steam trap management program. It's really a problem. That's not enough good traps, pure and simple. We like to see the reliability indicator where a site has had a sustainable steam trap management program every year. They're maintaining a high percentage of good traps. Above 75% good is kind of a benchmark. If you maintain above that, you should see less reliability issues. And the reliability issues we're talking about are problems caused by condensate, whether it's a water spray or a water slug fracture, extinguished pilot, recordable event from a slug tripping a flow meter. And oh my goodness, we don't want to talk about turbines, right? What's a slug of water going to do to a turbine? But when you take a look at eroded turbine blades, That didn't come from steam. It came from particles in the steam, either being debris or being condensate that hasn't been disentrained. When we take a look at turbines, we like to evaluate 7 points to see if there's adequate drainage needed in these 7 points. Sometimes people think, well, I don't want to look at so many potential traps on a turbine. Okay, but then what we typically see is this. It's a fog zone. It's an unsafe area, and it only means that we have to look at these 7 points to see if there's adequate drainage to avoid this. All right, now we're going to talk about steam heat theory. So some of you are going to think, wow, this is pretty elementary. It starts off elementary. Please bear with me. I wrote this article in the May of Chemical Engineering, and it's one of the attachments. It's also on the tlv.com website. I hope you have a chance to read it. Let's take a look at the very simple task of boiling water at 0 psig. And we're going to define a BTU as a 1 degree Fahrenheit rise in temperature of 1 pound of water at 0. So if we put in 1 BTU of heat, our temperature goes up 1 degree Fahrenheit. If we put in 2 BTUs of heat, it goes up 2 degrees Fahrenheit for each pound of water. And if we go and put in 60 BTUs, we have 92 degrees Fahrenheit. But conversely, we can subtract 32 from 92 and understand that we've got 60 BTUs per pound of water. And that's the beauty of putting a thermometer in water and being able to sense the heat. It's 92 degrees, which means it's 60 BTUs per pound. And we carry that all the way on to 212. 32 from 212 is 180. We can sense for boiling water, in order to get it to a boil, we have 180 BTUs of sensible heat. Easy to sense. Let's take a look at our boiler. And this is the equation for steam heat. It's the sensible heat that boils the water and the latent heat that evaporates the water. We're going to take a closer look at the latent heat. So here we have ice, and we've got to put latent heat to melt ice, 144 BTUs. Now we've got melted water. We're going to put in sensible heat to take that ice water and bring it to a boil. Now it's boiling, and we're going to put in latent heat, and we're going to get saturated steam by evaporating it. Great. And we're going to use that steam heat, but let's take a look at what we've done to make steam. We put in feed water and fuel into a boiler, but a boiler is not 100% efficient. So we're going to have some stack losses. But we've made steam, which we're showing as 100%, but that 100% is really 85% of our fuel usage. And then we're going to distribute it into the process and use it into the process. We're going to use 70% of that 85% energy. So really, from our fuel input, we only have about 60% of energy that can go into the process for the heating. And we are going to discharge condensate that's got about 30% of our steam heat, or about 20% of our energy input. That's a sizable number, 20% of our energy input. So we really want to take a look at economizers on boiler stacks, and we want to take a look at recovering condensate so we get the maximum energy efficiency of our steam heat. Now, the beauty about steam is it's very forgiving, but that's also potentially a problem because people don't realize it has to be proactively maintained in order to optimize the steam. You cannot optimize steam using equipment with suboptimal steam. And suboptimal steam creates risks. We want to mitigate the risk by optimizing steam. Let's take a look at a distillation unit and a distillation column. And what's our goal? We want to optimize the cut point. That's why we're in business, right? We want to get maximum return on investment. High quality production. We have to maintain a strong vacuum. But how do you get that vacuum? Why do we see this? Yes, it might be leaks, but it also could be poor quality steam ejectors. The motive steam goes here, the suction side comes here, the blending comes out here, and the animation looks something like this. But all steam is not created equal, and we certainly want to make sure that our motive steam is in the best quality possible to optimize those ejectors. So we're going to get fast steam flow to get lower pressure, and we don't want to change the nozzle diameter. But look at this on the side. What do we think caused that? Was that wire drawing caused by steam, or was it caused by water? Wet steam erodes the nozzle, which reduces the vacuum. And when you have nozzle or throat erosion, it increases the steam consumption and reduces the vacuum. And you want to know, well, how much? Well, here you go. A 7% nozzle diameter increase from erosion requires 28% more steam and it reduces the suction at the same time. So you're paying more and you're getting less of a benefit because you got wet steam on the ejectors. Doesn't it make more sense to make sure that you really optimize the steam quality going to those jet ejectors? It'll improve cut points or vapor removal, and that's going to make your operations optimized, or certainly support optimized operations. Let's take a look at making steam again. Why am I focusing on that? Because people know that you put sensible heat to boil it, and they say, yes, we understand that, Jim. Now the water's boiling, and we're going to put some latent heat in there, and we're forming steam, but it's wet. And then eventually we're going to get the saturated steam, and that's what we use in our plant, saturated steam. Well, here's the news flash. No, you don't. Let's take a look at varying dryness. Because what people say to me all the time, I've been doing this for like 43 years, and I can't tell you how many times people have come to me with this question. Jim, we're going to do pressure reduction from 200 psi or 150 psi to 15 psi. And we're worried because the total heat at 200 is 1200 BTUs, and it can only take 1164 BTUs at 15 psi. So take a look at what's going to happen, Jim. The sensible heat at 200 is 362, and at 15 it's 218. Well, the difference is going to cause me to have extra amount of latent heat than I need for saturated steam, and I'm going to get 71 degrees of superheat. So I guess in my design, I have to put in, I got superheated steam. I don't want superheated steam downstream, so I've got to put in a desuperheater so I can get saturated steam. Can't tell you how many times people have told me that, and I just sit there and say, okay, not really. That's a superheated steam fallacy. And here's why. When I go to a plant and say, what are your steam pressures? They'll say something like, well, we've got 600 superheated, and then we've got like 150 saturated steam, 75 saturated steam, 30 saturated steam. And I look and I'm thinking to myself, no, you don't. No, you don't. You don't have any saturated steam in your plant. You have superheated steam or you got wet steam. You don't have saturated steam. You got wet steam. People think they have this, and that's really the crux of the problem. That's really why I wrote the article in May. They think they have this, and then they don't worry about dealing with the water that's actually in their steam system. And that's why they have gap years in steam trap management. That's why they don't think about separation ahead of equipment. That's why they build up condensate slugs. They think they have this, but you never have saturated steam. You only ever have superheated or wet steam. And that's what I call the dry steam fallacy. So let's take a look at making steam again. You don't have saturated steam. You got wet steam. It comes off at the boiler about 95 to 97% dry, which is 3 to 5% wetness. You have uninsulated flanges. You have missing insulation. You have insulation that's only 80% effective. So it gets wetter as we go on. So is it 90%, 88%? Who knows? Slurries in Alberta can have 30% wetness in them. Now, I wrote this article in 2013 about beware the danger of cold traps, and the main reason was to tell people that the priority for steam traps should be to fix the block traps or the cold traps first. But I also included this table, and I hope that people take a look at Figure 1 if you see the article, which is also attached to the webinar. because in that table, I wanted to talk about regions of steam quality. People think they have saturated steam, but they really have probably 5 to 10% wetness, maybe more. They don't get the full amount of latent heat. They get a reduced amount of latent heat, which can increase their production time if they're putting water droplets into the heat transfer surface. Tracy's going to show you how to fix that a little bit later on in this presentation. So let's take a look at the steam dryness percentage. Let's take a look at the same animation I saw before. We're going to drop off the left-hand side, and we're going to focus on the saturated steam side. Oh, it's not saturated. The steam is not saturated, it's wet steam, and we want to know what the dryness fraction is. So really think of steam like this animation. You've got condensate that has to get removed. It's already been disentrained, but the steam contains a lot of wetness entrained in the steam itself. And you want to make sure that you can remove that. So if we take a look at the equation for steam quality, and that's your steam dryness. If you know what the dryness is, like 95%, 90% dry, that includes what the wetness is. You can use this formula if you're going to separate to see what your moisture separation is going to result. So if we take a look at the steam characteristics chart or the steam table again, and what you see is I've got at 200 psi different dryness fractions. So let's say that we're coming off the boiler at 95% dry. 1158 is the total BTUs, not 1200. Down here at 1164 would be saturation at 15 psi. So even such a large pressure drop with the steam coming off the boiler at 95% dry, 5% wetness, not considering any work through pressure reducing valves, not considering any radiation losses of the pipeline, not considering any flange effect where you have uninsulated flanges, you don't have enough steam to create superheat. You don't have enough energy to create superheat. Now, if your steam is at 90%, like 1116 BTUs, that's like going to give you wet steam at 95% downstream. That's just theoretical because you still haven't considered all these other losses. If you're using 90 or 95% steam going into different pieces of equipment, it's not going to allow you to optimize the production of that equipment. That's why we want to use high efficiency separation. It improves ejector reliability, turbine efficiency. If you've got critical molds, it's going to help improve uniform heating and your valve trim longevity. I mean, you get sonic velocities through valves, 88,000 feet per minute. I mean, you really don't want to have a lot of moisture exploding, in a valve. They don't call it exploding, they call it cavitation, but let's face it, that's really what's happening. The water is exploding in the vapor. Let's take a look at the impact on steam equipment. When you see extruder problems like this, or like this, for example, well, the first thing we want to take a look at is it properly trapped? But then the next thing we want to take a look at is it properly separated? It's not always enough, like for example, on the barrel heaters, to just put in the right traps or on the die plate. We want to make sure we got the good quality steam going to it. So ahead of that control valve, we might want to make sure that we've got a separator. And that's how you get quality pellets. All right, so take a look at this graphic on the left. That's what's going into your steam system. Do you think you can optimize the production heat or the production heat uniformity if you've got steam that's got entrained moisture in it, or that's with no separation of the entrainment? Or would you rather have a separator and see what you have on the right side? I can guarantee you that the right side is going to give you better uniform heating in probably most, if not all, of your heating applications. So now let's take a look at the real steam table when you take a look at your separation effects. On the left-hand side, at 200 psi, you see 838, 796 under the latent heat. This is different degrees of dryness. So 95% of dryness is 796, 90% 754. But if you can remove 98% of the water and use the equation that's in the article, then you see that you can get your steam quality up to 99.7%. That's essentially as close to saturated steam. It's not saturated, but it's as close to saturated steam as you are going to get into a production plant. So we always tell people with valve stations, why don't you consider to do this? Put a strainer and a separator before the valves. We commonly don't see that, but certainly for production equipment, it's something to consider. We commonly see this. At least in this case, they've got good trapping stations with adequate size collecting legs, even if they don't have a strainer or a separator, but they don't always do that. This is commonly what we see with an undersized trap collecting valve here, an undersized collecting leg here, and that valve is going to have reliability issues because all that water is going through that valve, and that is going to cut that valve trim. Okay, when we take a look at waste heat boilers, this is a tremendous area for wet steam. Waste heat boilers can generate a tremendous amount of wetness, and all we've got to do is put a separator and a trap station there with an engineered separator drain to remove the wetness. 98% removal gives us 99% dry steam. So if you're coming off of a waste heat boiler and going to critical process equipment, please make sure to consider a separator. Okay, we're talking about heating quality and risk mitigation in steam systems, so we have to talk about air. So if you remember Dalton's law, I'll let you read that. The sum of the pressure is the same as if each gas filled the same container by itself. It looks like this graphically. So here we go. Steam at 8.8 megapascal, 8 bar, 2 megapascal is 1 megapascal when combined. Why is that important? We're trying to transfer heat through a metal wall. So take a look at the center of this graph. There's the metal wall. We've got steam on the left side, product on the right-hand side, and we've got different films on the inlet side, such as Rusker scale and condensate drops or film. We want to minimize that. And if we minimize that and stagnant product and degraded product on the other side, we might get a temperature transfer of 225. But if we have an air film, it might drop the temperature down to 190. Okay, so I'm showing a homogeneous air film here. More realistically, the air film will probably be, heterogeneous mixed with the steam. But just to give you an idea of what type of an impact air can have, just 4/100ths of an inch of air film has the same resistance as 44 feet of copper. Just take a look at the difference in resistance or conductivity in marks, and you'll see what I mean. The simple solution is vent air. Now, where do we vent air? I got a steam trap and it has an air vent in it. Is that enough? Well, it depends. Because if you watch this animation, what you'll see is sometimes air is heavier than steam and sometimes steam is heavier than air. It depends on the pressure and the temperature. So it's not always enough to have a steam trap that has an air vent at the bottom of the piece of equipment. Because we don't know which is heavier, air or steam. Now, a good way to get air out of the system is taking a look at the end of the main, because when you start up a system, there's a lot of air in the system. And also, when you're condensing steam, it produces components of air. So don't just trap the end of the main. It's a great opportunity to collect all that air in a bottle and run it through an air vent. And of course, when you have an air vent, you have to pipe it safely to drain so it doesn't have any water mixture that can blow out on top of people. Let's take a look at optimizing a jacketed kettle. So here we have a steam trap at the bottom with an air venting function. And the steam is coming in almost the midpoint of the kettle. It's not coming in at the top of the kettle. Even if it were coming into the top of the kettle, it might be pushing air to the far reaches of the kettle at the top. When that air is at the top, you cannot optimize that heat. So the simple solution is to put an air vent on the other side, and then the air vent will remove the air from the system. And we want to pipe that vent safely to drain so it doesn't have vapor that spills on people. All right, so people think of a steam line like this. They see the pipe, they see the steam, but I'm always going to ask you to please consider what's inside. You've got entrained water that has to be removed through collecting legs, and you've got water droplets that's still entrained in the steam, and the water droplets have to be removed for the most effective heating. You don't have saturated steam ever in your plant. except returns close to saturation after a separator. What you have is wet steam, and if you deal with the wet steam, you will optimize the quality of your steam, and peace of mind starts with high quality steam. So that concludes my session, and now I'm going to turn it over to Tracy. Thank you very much.
Thank you, Jim. So to start our discussion of pressure reducing valves, the first question we should ask is, why reduce pressure? Well, firstly, steam is often produced at higher pressures because it may be required at those elevated pressures and temperatures for certain applications, but it also can be produced and distributed more cost effectively, especially since the required pipe size for a given steam flow rate will be smaller at higher pressures than at lower pressures. Additionally, reducing steam to a lower pressure can improve pressure stability downstream and, to some extent, the steam quality. It is generally understood that there is a direct correlation between the saturated steam temperature and pressure, and if processes are operating at lower temperatures, it follows that those process heating applications would probably not require high pressure steam. In fact, excessive steam pressure can sometimes lead to pressure and temperature control problems and subsequent inconsistencies in product quality. And finally, low pressure steam contains more BTUs per pound of latent heat than high pressure steam and can heat more efficiently. But when looking at actual pressure reducing applications, what we will often see is poor piping installations, wet steam system conditions, even the occurrence of water hammer events. This often leads to erosion of valve trims and piping, corrosion buildup on valve components and blockage of strainer screens, and in some cases, poor process control. So let's consider a simple PRV station supplying steam to a heating surface. Which of the following designs provide the most effective heating and reliability? Here we see a lot of wetness coming down to and onto the heating surface. Why is that? Well, no trap, no strainer, no separator, nothing to remove the moisture. We can improve that by adding a drip trap, which removes the water that has already fallen out of the steam. Notice that the reduced water film on the heating surface, but the steam still contains a lot of entrained moisture. Why is that? Well, no separator. Additionally, there is no strainer, which means rust or debris could cause the valve to malfunction. Now we've added a strainer, which improves PRV reliability, but there is still entrained moisture in the steam, which detracts from uniform heating of the process. For example, it could create cold spots or extend process heating times. That's the problem when no separator is included. Now here we have an optimized system, and notice the dramatic effect on the heating surface with optimized steam quality to the process. The only possible detraction is if there is not sufficient installation space. The COSPECT, with its 5-in-1 features, delivers optimized heating in the most compact space. Now a review of the principal types of pressure reducing valves used in steam systems. Steam pressure reducing valves, or regulators as they are also known, are grouped into two basic designs: direct operated and pilot operated. The direct acting PRV offers a lower cost, a simple and compact design, a high pressure reduction or turn down ratio, easy to install and adjust pressure, and is easy to maintain when needed. However, it has a smaller capacity range with less accuracy than pilot-operated PRVs, is subject to inverse response, and is generally recommended for applications that only require approximate pressure control. Here is an internal view of one particular model of direct-acting PRV. The key components of it are the adjustment handle for easy adjustment of the secondary pressure, the adjustment coil spring Many manufacturers offer their valves with different springs for a variety of primary and secondary pressure conditions. The bellows for a durable and packless seal between the wetted and non-wetted parts of the valve, and the main valve, which controls the flow of steam from the primary to the secondary side. This animation demonstrates the basic operation of the DR20 direct-acting PRV. In direct-acting pressure-reducing valves, the amount of valve opening is determined directly by the movement of the adjustment spring. If the spring is compressed, it creates an opening force on the valve which increases flow. As pressure builds downstream, equalizing occurs by feeding the downstream pressure to the underside of the adjustment spring against the bellows, where its upward force counterbalances against the spring compression. The adjustment spring compressive force, which opens the valve, is limited to allow sufficient spring sensitivity to equalize with downstream pressure changes. The net result is simple pressure control through a valve orifice, but where high flow rates result in a drop-off in secondary pressure. Offset is one of the principal disadvantages of the direct-acting valve. Ideally, we would like the PRV to maintain a desired secondary pressure, known as the set point pressure, across its entire capacity range. But due to the nature of the valve's operation, the secondary pressure will begin to fall as the flow rate through the valve increases, resulting in a certain amount of offset, or droop as it is often called. The amount of offset will vary depending on the particular model, spring range, and primary and secondary pressure conditions. This offset is unavoidable and should be taken into account when considering the level of accuracy required for the application. Pilot-operated pressure-reducing valves offer higher set point accuracy and a wider capacity range as compared with the direct-acting valves, but generally have a higher purchase and installation cost and a more advanced design. The two common types of pilot-operated PRVs are the diaphragm-actuated valves and the piston-actuated valves. Diaphragm-actuated PRVs consist of the same essential components of direct-acting valves, namely the main valve plug and seat, the diaphragm and the spring, with the addition of a pilot which separates P2 and the diaphragm loading force, PL. By doing this, PL can be controlled in relation to changes in P2, meaning that PL can be increased from P2. This allows the regulator to be more responsive to condition changes. Furthermore, the pilot requires an external sense line connected to the downstream piping. However, diaphragm valves typically have a large number of moving parts, which leads to lower reliability. They also are susceptible to internal damage during system upsets and exhibit limited response to variable flow and/or system pressure changes, which can cause pressure swings downstream. In piston-actuated PRVs, a piston rather than a large diaphragm is the actuating component that opens and closes the main valve. And unlike the diaphragm valves, the pilot valve and the primary and secondary sensing channels are internal to the valve, although some models have an option for external sensing, secondary sensing. This animation demonstrates the basic operation of the COS-R16 pilot-operated piston-actuated PRV. In piston-actuated pressure-reducing valves, the pilot valve loads the piston, which increases the downward force used to open the larger main valve. This enables larger flow capacity with a lower pressure offset. The opening and closing of the pilot valve is controlled by the balance of force between the adjustment spring and the secondary pressure in the same manner that a direct-acting valve operates. However, the opening and closing of the pilot valve purposely delivers pressure to the main valve piston or diaphragm. This pilot flow pressure then causes a downward force that is amplified by the area of the piston to enable opening of a much larger main valve, which in turn provides the ability for very high flow rates. Because the downward force is amplified through the use of a piston, A small change in the opening on the pilot valve can result in a large change in flow and downstream pressure through the main valve. As a result, there is little change needed in adjustment spring force on the pilot, which in turn provides quick response over a wide range of steam flow rates. Quick response and tightened delivered pressure control represent the main advantages of this type of valve. The TLV COSPECT valve features a 5-in-1 design, which consists of a pilot-operated reducing valve, separator, a steam trap, a strainer, actually two, one for the main valve and one for the pilot valve, and a noise attenuator, which is standard for the 2.5-inch size and larger, and optional on the smaller valve sizes. The primary feature of the reducing valve is the shock-absorbing piston, which contains a hemispherical design on the lower portion to enable a self-aligning movement, permitting smooth, responsive control of secondary pressure. Steam that enters the COSPECT valve first passes through the strainer screen and then through the supercyclonic effect separator, which provides dry steam through removal of 98% of entrained condensate in the steam flow, leading to 99.8% steam dryness as it flows upward to the reducing valve section. The improved dryness helps minimize erosion, improves heat transfer efficiency and rate, and leads to increased system reliability. The condensate removed by the SCE separator is then drained out through the SST free float steam trap at the bottom of the COSPECT. The free float trap provides instant and continuous discharge of condensate, a 3-point seating design for tight shutoff, even under no load conditions, and a 316L float for corrosion resistance and high reliability. Now let's look at a few key considerations when selecting among pilot-operated PRVs. All PRVs are not created equal, so let's look at the performance characteristics of 1-inch PRVs from various manufacturers. Manufacturer A shows a 15 psi drop from set value at a load of about 700 pounds an hour. Manufacturer B shows a drop of 15 psi at a load of 1,000 pounds an hour, but at 700 pounds an hour load, the drop-off is only about 6 psi. Manufacturer C maintains close control through 900 pounds per hour load, and then control rapidly drops off from the set value, but it has good control through 900 pounds an hour. The TLV's 1-inch COSR has excellent control through 1,400 pounds an hour. Not all 1-inch valves are created equal. Tight control performance is essential on critical process applications. So which valve would you prefer to use? Manufacturer A, Manufacturer B, Manufacturer C, or the COSR? Some pressure-reducing valve manufacturers offer the option of external or internal secondary sensing. Each PRV must be installed using one of these two methods, but the choice may depend on a few factors. For instance, using external sensing, maximum valve capacity can be achieved even under critical flow, high turn-down conditions. But to be used effectively, the external sensing pipe must be continuously downward pitched with no low points where condensate can collect, as this could prevent proper sensing of downstream pressure and create pressure stability problems. The point at which the sensing line connects to the downstream piping is also important. It should tie into the upper portion of the piping, preferably in a section of straight piping, typically 10 to 20 pipe diameters from the PRV outlet. By contrast, internal sensing is preferred for installations with limited space between the PRV outlet and downstream equipment, or where no sensing point is available downstream of the PRV. Additionally, use of internally sensed PRVs lowers the overall installation cost. However, the maximum capacity of the valve may be somewhat reduced at high turndowns. For the COSPECT series, an internal conversion is required to ready the valve for internal sensing. Noise is another issue that can be of significant importance. High turndown in pressure and/or high steam flow rates can generate excessive internal noise. And in many cases, noise levels from steam PRVs and control valves can exceed the OSHA recommended 85 decibel time-weighted average threshold, in which case noise mitigating measures and/or hearing protection may be required. Some relatively common options for reducing valve noise include installing acoustic silencers after the PRV, installing muffling orifice plates in downstream piping, enclosing the valve in noise reduction jacketing, or simply using a larger size PRV. But any one of these methods can add appreciable cost to the installation. As was mentioned earlier, one feature of the COSPECT series of PRVs is that the larger size models already include an integral silencer. This helps to reduce noise level by approximately 10 to 20 decibels below most other PRVs, and in many cases, the noise level will be safely under the 85 dBA threshold. This in turn can potentially eliminate requirement for hearing protection, and not having to use other noise reduction equipment helps to lower the installation cost. When it comes to sizing a pressure reducing valve, we not only have to determine the proper valve size, but the primary and secondary pressure piping of the valve as well. So let's start with a set of given operating conditions, which are primary pressure of 100 psi saturated steam, a desired secondary pressure of 30 psig, a maximum steam flow of 1,500 pounds an hour, and a target steam velocity in the piping of 100 feet per second. From this, we need to determine the inlet and outlet pipe size when we're using Schedule 40 piping, and of course the PRV model and size to install in the line. We first start with the piping. To determine the proper pipe sizes, we can solve for the cross-sectional area of the pipe as shown in this formula, which requires that we know the specific volume of the steam at the steam pressure in the line, the maximum steam flow rate, and the target steam velocity. And so for the inlet piping, we calculate a cross-sectional area of 2.33 square inches, and for the outlet piping, the area is 5.68 square inches. Here is a table of nominal pipe sizes and their respective cross-sectional areas for 3 different pipe schedules, which correspond to different pipe wall thicknesses. Our application involves using Schedule 40 piping, so we look at the range of areas and first find the inlet pipe size that would have a cross-sectional area of 2.33 square inches. This value falls between the listed values of 2.04 and 3.36. Since we don't want to undersize the line, we of course choose 3.36, which corresponds to a nominal pipe size of 2 inch. And so our inlet piping will be 2-inch Schedule 40. For the outlet piping, our required cross-sectional area is 5.68 square inches, and this falls between the listed values of 3.36 and 7.39. This means we would choose 7.39, which corresponds to a 3-inch nominal pipe size. So our outlet piping will be 3-inch Schedule 40. Another way to determine the required line size is quick and easy is to use TLV software. The TLV engineering calculator is available to use on the TLV.com website, and the TLV Toolbox app can be downloaded to a cell phone from the same website. Using the pipe sizing by velocity for steam option from the online engineering calculator, we input the sizing data provided and come up with a calculation of course, 2-inch pipe size for the inlet side, and 3-inch for the outlet side, just as we had calculated previously. So now that we have the inlet and outlet pipe sizes, we can proceed with sizing of the pressure reducing valve. In most cases, the first step in sizing a PRV is to select the proper adjustment spring range, which often determines the model of PRV to use. This table shows the various TLV COSR models with their respective spring ranges and available valve sizes. Using our sizing example, we have an inlet steam pressure of 100 psig and a secondary of 30 psig. These pressures fall in line with the spring range of the model COSR16 PRV. Next, we must determine what size of COSR16 to use. For that, we use the capacity table shown here. Because of the small print, which would be hard to read from the slide, I will expand the relevant sections of the chart so we can follow the example. In the heading at top, we have the primary steam pressure, the secondary pressure or pressure range for both external and internal sensing, and then the nominal valve sizes in increasing order from left to right. The capacity values for the given primary or P1 pressure of 100 psi are below, with the respective capacities of each valve size based on various secondary or P2 pressures. So for a P1 of 100 psi and using external sensing, a P2 of 30 psi, we need to read across the available capacities until we find one that meets or exceeds our maximum steam flow rate of 1,500 pounds an hour. Did you find it? The first value that meets our maximum steam flow rate of is 1,805 pounds an hour. To find the valve size that provides this capacity, we simply read vertically up the column to find the PRV size at the top, which is the 1-inch size. Therefore, a 1-inch COSR16 is the model and size required. And if you compare this capacity with the 1-inch COSR performance curve we looked at earlier, you can now see that the capacity is somewhat higher with the use of external sensing. So we now have our PRV and our inlet and outlet pipe sizes determined. But is this all there is to the basic PRV station? Aren't we forgetting something? Remember our discussion earlier? What about including a Y strainer before the PRV to remove rust, scale, and other debris from entering the valve, and including a blowdown valve on the strainer to facilitate clean out of the debris during startups or whenever necessary? Don't we need pressure gauges around the PRV station to monitor pressure on both primary and secondary sides and to be able to adjust the set pressure? We know this is saturated 100 psi steam coming to the valve, so according to Jim, that means it's probably wet steam, right? Shouldn't we take care of the gravity drain condensate that reaches the PRV station by adding condensate drainage legs and traps to each side? And don't forget safety. To protect downstream piping and equipment from overpressurization should the PRV fail open, we should have a safety relief valve installed a short distance downstream of the PRV, set to lift at an appropriate maximum pressure level, and capable of handling the full capacity of the PRV. But really, for a complete PRV station, we should improve the steam quality further by achieving at least 99.8% dry saturated steam by removing entrained moisture in the steam flow using a 5-in-1 COS16 valve, which includes the SCE separator and free float trap. Now let's look at a few examples of pressure reducing valve applications. The first is really an extension of the application example we just discussed. It is essentially a one PRV station followed immediately by another PRV station, two PRVs in a series arrangement. The first PRV to drop the pressure from a high to an intermediate pressure, and the second to take the intermediate pressure to a lower pressure. Typical characteristics of series reducing stations are that they are often used for very large pressure turndowns, where one PRV cannot take the full pressure drop. And in some cases, the intermediate pressure may also be used to supply steam to a separate set of applications. Some common applications for two-stage reduction are building heating or HVAC systems, the aerators, which typically require makeup steam pressures of 5 to 10 psig, and other low-pressure applications. Lead lag reducing stations typically consist of two valves in parallel, both valves supplied by the same primary pressure and both controlling the secondary pressure, but at slightly different set points, such that the two PRVs don't fight each other trying to control the same exact pressure. This arrangement is used in applications where there can be wide variations in steam demand from one moment to the next, such as when large steam using equipment is suddenly turned on and off, or from one season to the next, often referred to as summer-winter loads. The smaller, or lead valve, typically operates continuously and handles the smaller load conditions by itself. But during increased steam demand conditions, the smaller valve may not be able to maintain its set pressure, and the secondary pressure droops to the set point of the larger or lag valve, which then starts delivering steam at a higher flow rates to maintain the secondary pressure at the slightly lower set point. The lead-lag arrangement can help reduce the risk of valve chatter from a single large PRV trying to maintain a very low flow condition. The most common application for these PRV stations is for building HVAC systems. Autoclaves are a relatively common application for steam pressure reduction. They can be found on hospital sterilizers, vulcanizers for curing rubber products, retorts or pressure cookers for cooking food, and many other pressure chamber applications. What these various autoclaves typically have in common is that they are batch processes in which the product to be heated is in a closed chamber pressurized to a particular steam pressure and temperature. In most cases, dry steam is required to avoid condensate droplets from getting on the product and negatively impacting the product quality. Additionally, the chamber is initially filled with a large volume of air, so the air must be purged or vented from the autoclave to allow for an even steam temperature throughout. This image shows one type of autoclave with a COS16 PRV for fixed secondary pressure to the chamber, with an LA21 thermostatic air vent to help vent air both at startup and during operation, and a JX series free float trap to drain condensate from the bottom of the chamber. If remote operation or multiple programmable set points are required, the MC-COS series is available with an actuator for automatic pressure adjustment and can optionally be provided with a programmable controller and pressure transmitter. Alternatively, if pneumatic control is preferred, the PN-COS series can be set up to operate with a compressed air supply in a variety of ways, with or without a programmable controller. One case study involving the use of the COSPECT pressure reducing valve was at a rubber vulcanizing autoclave at a North Carolina plant. The challenges for the plant were entrained moisture in the steam supplied to the autoclave. The condensate droplets were collecting on the surface of the rubber, causing crater-like defects. This reduced the strength, durability, and the aesthetic appearance of the material. The product reject rate was at times as high as 50% of their production. Additionally, the PRV they were using at the time required frequent maintenance to keep the equipment operating. To deal with these problems, they installed a COSPECT valve. The product quality from that point dramatically improved, and the product reject rate dropped to about 5%. Another application where PRVs are often used is on low-pressure steam coils for heating air. Typical applications might include process air coils for heating or drying a product, combustion air preheat coils at the boilers, and building heating systems. Most of these applications might also include a temperature control valve, which modulates the flow of steam to the coils to control the exiting air temperature. One latex products manufacturing plant in Alabama was using a temperature control valve on a 110 psi steam supply to dry the product at a particular temperature using steam coils. The problems they were having were variations in steam pressure and temperature to the coils, and productivity and product quality were below what was expected. The corrective measures included installing a COSPECT PRV upstream of the control valve and reducing the pressure to 40 psig. The drying time was able to be held to the desired level, enabling improvements in both product quality and production rate. There are many other examples like these where improvements in productivity, product quality, and reliability have been achieved by utilizing the 5-in-1 features of the COSPECT valve. So we want to thank you for joining us today. And if you have any questions about steam system applications, our Consulting and Engineering Services Group in North America can be reached by phone at 1-800-TLV-TRAP or by email at ces@tlvengineering.com. If you're not in North America, we do have 14 global offices, so please feel free to reach out to your local TLV office to ask any questions or inquire about how TLV's Consulting and Engineering Services Group can help you with your steam systems applications. We also encourage everyone to visit our tlv.com website, where you can find links to an online calculator, many technical articles, and other technical training resources, as well as this webinar recording and recordings of other webinars that have already been conducted. We'll turn our cameras back on now. And Jim and I want to thank you again for attending this presentation. We hope that you enjoyed our webinar in eliminating hidden risks in your steam supply and pressure reduction systems, and we hope that you'll check out our website periodically for postings of future TLV webinars. And a special thank you to Justin McFarland for creating many of the graphics for this presentation. Have a great weekend, everybody. Bye.